This is my Calculus 1 course. Today we're going to learn how to find the derivatives of exponential or logarithmic functions. And we're also going to continue to practice the differentiation formulas. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. The primary purpose of this course is to learn how to find the derivatives of functions. And I've got good news for you. When you finish this class, you'll have accomplished that goal. It's like preparing to do a job, and you have to get all your tools together before you can perform the job. Well, we're at that point in this course. Now that you learned how to find the derivatives of functions, you have all the tools that you need to continue throughout the entire calculus curriculum. The point that I'm trying to make here is that this course is based on everything that you've learned to this point in the course. All these derivative formulas are really the only thing that we need to proceed throughout the calculus curriculum. So we've set a foundation for you. You have all of your tools, and we're ready to go. So again, this is a very important part of the course. If you've followed along and done all the homework assignments, then you have all the tools that we need to really pick up momentum in the calculus curriculum. So you may want to get a picture of the exponent rules. And of course, you should have a picture of all these formulas here. You're going to need those as we continue throughout this course. So you should have those right in front of you. If you didn't take a picture of those, go back and take a picture. You probably have a number of those formulas memorized by now, which is good. But if you forget, you're going to need those right in front of you. So, as I mentioned in the previous class, the chain rule is typically very confusing for students, and the only way to solve that problem is to continue to use the chain rule. And I know you're probably at the point where you really don't want to use the chain rule anymore, but like I said, you can't escape it. We need to get more and more and more practice with the chain rule, and so we're going to do that today. But we're also going to review the quotient rule and the product rule. It's vital that you know how to use those rules throughout this course. So I know you're probably tired of having to do this, but we need to do more of it. So let's get into it here. And when we're done practicing these formulas, we're going to go on to some other things in this class. So we have a function within a function. And this is a different type of problem that we haven't really seen. We're going to use the same differentiation formulas, but every problem that we do has a slight difference. So we're not just doing the same problems over and over again. Because we have a function within a function, we're going to use the chain rule. So we're going to find the derivative of the outside function using the power rule. So we found the derivative of the outside function. And we're going to, and we kept the inside function, and then we're going to multiply by the derivative of the inside function. So remember, there's 3 steps. When finding the derivative of a function where we have to use a chain rule. So first step, find the derivative of the outside function. Second step, keep the inside function. And third step, multiply by the derivative of the inside function. Now you don't have to write every single step that you're seeing here. you don't have to write d over dx. You can just find the derivative of that and just immediately write it. Okay, so now we're going to find the derivative of this expression, but notice that that is going to require the quotient rule. So the quotient rule tells us that we find the derivative of the numerator of that fraction, the numerator of this fraction, and then we multiply that by the denominator. Then we subtract the numerator of the fraction multiplied by the derivative of the denominator. And then we divide all that by the square of the denominator. So the derivative of that fraction is all of this purple stuff here. Okay, so sometimes in calculus you do get problems that are pretty complicated when it comes to the algebra. So you do need to be psychologically prepared for these types of problems. Just try to get it done as quickly as possible. And the derivative is 3x squared plus 2. We found the derivative of this and put it there. Okay, so let's go back and double check, make sure we didn't make any mistakes. When you're doing problems that are this complicated, it's very easy to make a mistake. And if you make one mistake, the whole thing is going to be wrong. So it's very important that you go back and check. Now, a lot of teachers would be okay with you just stopping there. The general rule in math is you want to try to simplify things, simplify your answer as much as you can. But some teachers don't really care because it just takes up time. You know, it takes time to simplify things, and students typically have problems with the algebra. But there's a number of reasons why you would want to continue to simplify. And one reason is you need to know the algebra. You need to be able to do the algebra, because sometimes problems require you to simplify the algebraic expressions. Also, if you're using some textbook and you do a problem like this and you want to check your answer in the back of the book, the answer is not going to be written this way. It's going to be written in a number of different ways, and so you need to know how to work with the expressions. So we're going to continue with this expression, and I'm going to use exponent rule number 4 on this fraction here. So when you have a fraction raised to some power, that's equal to the numerator raised to that power divided by the denominator raised to that power. That's exponent rule number 4. So you can check that here if you want. It's exponent rule number 4. And I'm going to distribute the 12x. So we have 12x to the 4th plus 24x squared minus 96x. And then we're going to have to use FOIL there. So we have 18x to the 4th plus 12x squared. I'm not going to add the inner terms yet. Of course, we can add these inner terms, but I'm just going slow here. Now, I want to point something out that's very important. And that is that, notice I wrote parentheses here. If you don't write parentheses, then you're going to get the wrong answer because we're subtracting all of this. This subtraction symbol applies to all of this. So it's almost a guarantee that when students first learn these problems that they have sign problems. They write the wrong sign on these terms. So I'm just letting you know that that's something you can expect. So we can combine these expressions. We're multiplying fractions, multiplying one fraction by another fraction, so we just multiply the numerators, which we're not going to do right now because that would be too complicated. And we can multiply the denominators. Now if we multiply the denominators, we get x cubed plus 2x minus 8 to the 5th power. That's using exponent rule number 1. We're just adding the exponents. And so let's simplify this stuff up here. 12x to the 4th minus 18x to the 4th is negative 6x to the 4th. And 24x squared minus 12x squared is 12x squared, and then minus 15x squared is negative 3x squared. And then we have minus 96x and minus 10. So you really have to be careful of the signs when you do a problem like that. Please be careful because it's so easy to write something that is incorrect. So then we have 6x squared plus 5 to the 3rd power times 4. And typically you're not going to see the form written like this because we have all these green negatives that you can pull out. So typically, well, it's more likely you're going to see the answer written in this form when you check in the back of textbooks and so on and so forth. So this is one possible form that you might see if you check your answer. But just be aware that the form might not be written this way. It might be written in a slightly different way. And so that's one really big problem that calculus students have, is that when they check their answer, it doesn't look anything like what they wrote. But that doesn't necessarily mean that your answer is wrong. It just means that the textbook writer or whoever was working for the textbook writer wrote the answer to that problem in a different form. But it's very possible that your answer could be wrong also. So that's why it's very, very difficult for calculus students to check their answers when it comes to these particular problems, especially the problems that use the quotient rule. So there you go. That is the answer for number 1 there. And I want you to try a problem like that. Go ahead and attempt number 2. You can use number 1 to help you. We have a function inside another function. So you have to use the chain rule, but then you have to use the quotient rule like we did in this purple part here when you multiply by the derivative of the inside function. So try number 2, and when you come back, we'll do it together. All right, we're back. Okay, so you can use dy over dx, or you can use y prime. So I know that problem was kind of tedious, but sometimes you do get some tedious problems in calculus. So if you got that right, excellent. Okay. So now we have similar problems, but now we have a root. Again, we have a function inside another function. So let's do this problem together, but remember, we can't do this problem unless we change the root to an exponential expression. So it's going to be raised to the 1/2 power. So we have not found the derivative yet. We have not found the derivative. We just changed to 1/2 power. But now we're going to find the derivative. Using the power rule, we'll find the derivative of the outside function. that's the derivative of the outside function. But notice we kept the inside function unchanged. That's what the chain rule tells us. And then we're going to multiply all that by the derivative of the inside function. So that is the chain rule. But when we use the chain rule in this problem, we see that we have to use the quotient rule when we multiply by the derivative of the inside function. So we're going to use the quotient rule. So we found that we need to find the derivative of the numerator and then multiply that by the denominator, and then we're going to subtract the numerator multiplied by the derivative of the denominator. And again, students typically have a lot of problems with signs, issues with writing the correct sign, so you need to be really careful when you do the algebra when you're using the quotient rule. Then we divide all that by the square of the denominator. So all of this is the derivative of the inside function. Alright, so you probably want to double check all that. There's so many steps and so many things that can go wrong. If you're not double checking constantly, then that's just a recipe for disaster. So you need to go back and check every single thing you write. Go back and check, go back and check, go back and check. Typically students want to rush through this, which is natural. You want to get it done. Don't do that, because you're just going to end up wasting more of your time. So I'm going to go ahead and change this. We have a negative exponent, so I'm going to bring that down to modify this expression here, because we have a fraction exponent, so we have to deal with that fraction exponent also eventually. So the derivative of this expression here is 4 minus 3x squared, and the derivative of this expression is 15x to the fourth. And that's all divided by 3x to the fifth plus 1 squared. We have to do some algebraic gymnastics here, it looks like. You don't want to turn this into a root quite yet. I was talking about getting rid of the fraction exponent, but now I see that probably best that we don't do that at this point. So this is where things do get kind of intense when it comes to the algebra. So we're going to use exponent rule number 4, which tells us that we can raise the numerator and the denominator both to the 1/2 power. That's exponent rule number 4. Now again, if you forgot the exponent rules, they're right here. Again, you're probably noticing that we need those rules. If you don't know those rules, you're not going to survive in this course. Let's distribute, or we'll distribute over here, and we'll use the FOIL algorithm here. So we have 12x to the fifth plus 4 minus 9x to the seventh minus 3x squared minus 60x to the fifth and then plus, actually I'm gonna keep the parentheses there, 60x to the fifth minus 15x to the seventh. So we're multiplying two fractions, and the easiest way to do this is to go ahead and multiply the denominators and the numerators rather than just simplify this complex fraction But be aware there's a lot of different ways to do this. Now let's simplify this expression first. So negative 9x to the 7th plus 15x to the 7th is 6x to the 7th. Then we have 12x to the 5th minus 60x to the 5th, which is negative 48x to the 5th. And then we have negative 3x squared plus 4. So we took care of these. We got all that condensed. And that's all divided by 3x to the 5th plus 1 squared. Now, again, what we're going to do is just multiply the denominators. So we're going to end up with 4x minus x cubed to the 1/2 power over 3x to the 5th plus 1 to the 1/2 power. And the 2 is still going to be down there. So again, we're just multiplying the numerators to get this, and we multiply the denominators together to get this. And let's double check everything, make sure we got that right. Everything looks right. So I'm going to copy this and go on to the next step up here. So notice we have exponential expressions with the same base. And this is in the denominator, so we can actually subtract these exponents. That would be the equivalent of x squared over x to the 1/2 power. Well, that's just x to the 2 minus 1/2 power, right? So that's all we're doing. There's a number of different ways to do this, like I said, but we're just using the fastest method as we show the steps. So we have 3x to the 5th power plus 1 raised to the 2 minus 1/2 power. Obviously, you don't have to show the 2 minus 1 operation there. You can just do the math, or the 2 minus 1/2 operation. So now, again, we just need to continue to simplify. And again, I'm showing that 2 minus 1/2 just so we can know how we did that. But that's a lot of work just to show that one operation. So I'm just going to copy and paste. Again, you don't have to show every single step here. So then we have a 3/2 power here. And so now I think we're ready to write our final answer. So I know what you're thinking. You're thinking that was really painful. That's a lot of stuff we have to write. But that's one of the reasons that calculus has a reputation for being so difficult, is because you're expected to know the algebra. You're not only expected to know basic algebra, but you're expected to know really, really complicated algebra. You're expected to be very, very, very good with the algebra, and most students are not. They're not at that level. And so let's double check all this. Okay, so there you go. That is the answer for problem number 3. So take a picture of number 3 and use this to help you with number 4. Go ahead and try number 4. Again, we have a function within another function. So you have to use the chain rule, but you also have to use the quotient rule when you multiply by the derivative of the inside function. And remember, before you find the derivative, you need to change the expression so it's raised to the 1/3 power. So go ahead and do that problem, and when you come back, we'll attempt it together. All right, we're back. So if you got that right, excellent. Remember, we can't leave our answer with negative exponents or fraction exponents. Okay, so are you going to get a lot of those problems? No, you're not going to have a lot of those. So don't get too depressed by having to do all that algebra. So now we have an expression that is the product of three things, and we have to find the derivative of that function. So in order to do this, obviously we have to use the product rule, but because we're multiplying three things, that makes it a little bit more complicated. So what you can do is you can consider 2 to just be a constant multiplier and use the constant multiple rule. So the derivative would be this times whatever the derivative of this expression would be, and you'd have to use the product rule here. That's not a very common way to do it, though. Probably the most common way is just to consider 2x to be the first expression in the product and sine to be the second expression, and then you use the product rule. So again, this would be in the product rule, this would be the first expression, this would be the second expression. But you can also combine the 2 and the sine. Then 2 sine x would be the first expression in the product, and x would be the second expression. So there's a lot of different ways you can do this, but I'm just going to consider 2x to be the first expression in the product, and sine to be the second expression. So now when we use the product rule, we're going to find the derivative of the first expression and multiply it by the second expression. So the derivative of the first expression in the product multiplied by the second expression in the product. Then we're going to add the first expression in the product multiplied by the derivative of the second expression in the product. So we get 2 times sine x plus 2x times cosine x. So that became that, and this became that. So you're going to encounter this situation quite a bit. I want you to try number 6. We have a similar problem. So remember, there's a number of different ways you can do this, but probably the easiest way is to consider negative 4x squared to be the first expression in the product and cosine x to be the second expression. You don't have to do it that way, but that's the way that I'm going to do it. So try number 6. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. So now we have the product of three things again, and we can consider this constant to be with the x cubed, and the blue and the purple expressions, we'll consider those to be the expressions that we're considering in the product rule. So again, this is a complicated situation when you have the product of three things, and in this situation we have to use the product rule twice. We didn't have to do that in these problems. We could have done it considering the constant to be a separate expression, and the product rule still would have worked, but we don't typically do it that way. We use the constant multiple rule. But in this example, we actually do have to use the product rule twice. We have to use the product rule 2 times because we have a product of three things. So I'm just going to rewrite this just so we know exactly what is happening here. I'm considering this to be one expression in the product, and this is another expression, and tangent x is another expression. So now we have to use the product rule, but the product rule only works when we have two expressions multiplied together. At least when we first use it, we have to think of it that way. I'm going to consider all this to be the second expression. I'm going to use brackets. And I guess I can get rid of these parentheses, and I'm just going to consider, again, negative 10x cubed to be the first expression. So we're going to multiply the derivative of the first expression by the second expression. And then we're going to add the first expression multiplied by the derivative of the second expression. And I'm just using brackets to try to make things clear. You don't necessarily have to use brackets. So the first part is going to be easy because the derivative of negative 10x cubed is just negative 30x squared. So we're done with this expression here. That was the easy part. But this is the hard part because we have to use the product rule a second time. So we have a product of two things, so I'm going to find the derivative of the first expression in the product, and then multiply that by the second expression. And I'm going to add the first expression in the product multiplied by the derivative of the second expression in the product. So we're using the product rule again. And so I'm going to rewrite all this stuff at the front. And the derivative of x minus 1 to the fifth, we have to use the chain rule. So not only are we using the product rule twice, but we have to use the chain rule. So we have the derivative of x minus 1. So we found the derivative of the outside, and we kept the inside, and we multiplied by the derivative of the inside. And then that's all multiplied by tangent x. And we have to find the derivative of tangent x, which would just be secant squared x. So let's go back and double check all this stuff. Everything looks right. So now let's rewrite. And I'm going really slow here. You can skip a lot of these steps. So we have 5 times x minus 1 to the fourth. Derivative of that would just be 1. And all that is multiplied by tangent x. And that derivative became that. So we're getting close here. So are you going to encounter a lot of these problems? Well, you are going to see them. It's fairly common to see complicated problems like this. You're not going to have to do a problem like this very often, but it's almost a guarantee that you will see it. You'll see problems like this in the calculus curriculum that you'll be expected to do. So you can't really escape this. So I'm distributing negative 10x cubed to this expression and this expression. So then we get negative 10x cubed times x minus 1 to the 5th times secant squared x. And I think that's it. So you're probably thinking that I'm making this difficult on purpose for no reason. The calculus doesn't have to be this difficult, but actually, yes, you are going to be expected to do this type of algebra. Not in every problem, but you are going to be expected to do a lot of problems that require intense algebra. So get a picture number 7, and I want you to use that to do number 8. And remember, we can't find the derivative unless we change x to x to the 1/2 power. And our instructions are simply to differentiate. So you can call this y prime or dy over dx. It doesn't matter. You also have to decide how to use the product rule when you first proceed. Is this going to be the first expression and this is the second expression? Or is this going to be the first expression and this is going to be the second expression? That's the way that I would do it. So if you're going to do it that way, then you might want to draw brackets so we can see exactly how we're going to use the product rule. You'll get the same answer either way, but this is the way that I'm going to do it. So you have to use the product rule, and then when you find the derivative of this expression, you have to use the product rule again. So go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. And there you go. So if you got that answer, excellent. So will you have to do a lot of these types of problems where you have this amount of algebra? You won't have to do a lot of them, but you will have to do them. You'll see them and you'll be expected to be able to figure out the algebra. So again, you can't escape this. You need to know algebra really, really well in your calculus courses. Okay, so if you got that right, excellent. So now we're going to go to some easier problems. Give you a break from those. I want you to be aware that oftentimes you can simplify expressions before finding the derivative, and that makes it easier to find the derivative. A lot of students would see this expression and think, well, I have to use the product rule. Well, you could use the product rule. But why would you do that when you can simplify first? I'm going to distribute the x to the 4th, use the distribution property, and I get negative x to the 9th plus 2x to the 5th. And it's going to be a lot easier to find the derivative of this expression than this expression, because I don't have to use the product rule anymore. So again, we didn't find the derivative, we just distributed, but now we can find the derivative, and we're done. So if you use the product rule here, you would get the same answer, but we don't want to use the product rule unless we have to. So there you go. Now I'm going to try another one of these problems. Here's another example where we could use the quotient rule, but why would we want to do that when we can just simplify first? So remember, when you're dividing a polynomial or any kind of algebraic expression that's a sum or a difference by a monomial, you can just divide each term in the sum or difference by that monomial. That's a very important algebraic principle. It's actually more of an arithmetic, just a basic arithmetic principle. So now we use exponent rule number 2. Now we could write this as 5 over x squared. And we could keep this as negative 8 over x cubed. But the problem with that is we'd have to use the quotient rule. We don't want to use the quotient rule if we don't have to. So why not just use exponent rule number 2, and consider this x to the first power using exponent rule number 6. So we'll just subtract the exponents and we get 5 to the negative, 5x to the negative 2 power. So again, just 1 minus 3 is negative 2. And then I'm going to bring this up using exponent rule number 8. Again, so we can avoid using the quotient rule. I don't want to use the quotient rule if I don't have to, because the quotient rule is kind of complicated. So again, we can use the quotient rule, but we don't want to if we don't have to. We can just use the power rule now. So we have 10 minus 10x to the negative 3 plus 24x to the negative 4. Okay, but remember, we can't leave our answer with negative exponents. So our final answer is going to be 10 minus 10 over x cubed plus 24 over x to the 4th. So there you go. So again, in this problem, it seemed as though we were going to need the product rule, but we didn't. We just distributed. In this problem, it seemed that we needed the quotient rule, but actually we just simplified and we didn't have to use the quotient rule. So I just want you to be aware that you can sometimes simplify the expression before finding the derivative. So take a picture of numbers 9 and 10, and I want you to try number 11. When you come back, we'll do it together. You want to simplify this expression before finding the derivative. Okay, we're back, and we're done. So that was a lot easier than using the product rule. So I want you to try number 12. Simplify the expression before finding the derivative. You don't want to have to use the quotient rule. And when you come back, we'll do it together. Okay, we're back. And that is our final answer. So if you got that right, excellent. So here's some more examples where we can simplify the expressions. You don't want to use the quotient rule here if you don't have to. So let's change that to x to the 1/2 power. And we'll change that to x to the 1 power. And again, when you're dividing a sum or difference by a monomial, you can divide each term in the sum or difference by that monomial, that one term. So this is basically fraction decomposition is the technical name for this. So now we're going to use exponent rule number 2 and subtract the exponents, so we get x to the negative 1/2. And here we can use exponent rule number 8 to get x to the negative 1. Now we can find the derivative. So we get negative 1/2, x to the negative 1/2 minus 1, and you can show this if you want, but you don't have to, and plus x to the negative 2 power. So bringing the negative 1 down in front, and then subtracting 1, we get negative 2. When you bring the negative 1 in front, it turns to a positive. So now we have z prime of x is equal to well, I'm gonna go ahead and show that. So then we have negative 1/2 x to the negative 3/2 plus x to the negative 2. Now we can't leave our answer with negative exponents or fraction exponents. So I'm going to change to negative 1 over 2 times the square root of x cubed and plus 1 over x squared. So there you go. So that's a lot easier than using the quotient rule. So I want to make it very clear, you're expected to know how to do this algebra. You're expected to know how to use the exponent rules. And most students are not really comfortable with the exponent rules. That's the problem. That's why calculus is so difficult traditionally. Now we have another example where we have a product. And your instinct might be to use the product rule, but why do that when you can just simplify the expression first? So now we're going to distribute, and we get x to the 14 thirds power plus 5x to the 5 thirds. So we used exponent rule number 1 here, and now we can find the derivative without using the product rule. Again, you don't have to show this, but I'm trying to go slow here. Okay, so we have 14 thirds x to the 11 thirds plus 25 over 3 x to the 2 thirds power and we can't leave our answers with fraction exponents, so we can convert to the cube root of x to the 11th power, and we can convert to the cube root of x squared. So I want you to try some problems like that. Get a screenshot of number 13 and number 14, and I want you to try 2 problems like that. Try number 15 first. Again, you want to simplify using the exponent rules, and just in case you are having some trouble with the exponent rules, I'm going to give you another chance to take a picture of those rules. You're expected to know every single one of these rules throughout the calculus curriculum. So go ahead and try number 15. You want to change this to a fraction exponent, and then you want to use exponent rule number 2 to simplify this expression before finding the derivative. You do not want to use the quotient rule. You could use the quotient rule, but why do that? Why make things difficult for yourself? So try number 15. When you come back, we'll do it together. Okay, we're back. So there you go. If you got that right, excellent. Okay, so you don't want to use the product rule for number 16. You can do it, but you don't want to. You want to simplify this first. So you want to change x, you want to change the 4th root of x to x to the 1/4 power and distribute. So try number 16. When you come back, we'll do it together. Do not find the derivative before you simplify the expression. Okay, we're back. So if you got that right, excellent. Okay, so we did a lot today. We're not done, but we did some really complicated problems to practice the chain rule and the quotient rule and the product rule. And we also learned how to simplify expressions before we find the derivative. You don't want to get fooled into using the quotient rule or the product rule when you don't really need to. So just be aware that sometimes you can simplify expressions before finding the derivative. Okay, so now we're going to find the derivative of exponential functions and logarithmic functions. So once you learn these formulas, you're going to have most of the tools that we need to continue with the entire calculus course. as I mentioned in the first part of the class. So I know you're probably sick of getting more and more differentiation formulas and having to memorize them, but these are going to be really the last ones that you're going to have to memorize. There might be one or two other ones, but we've learned really 99% of the formulas that you need to know, at least after we learn these. So if you want to find the derivative of an exponential expression, a is just some number greater than 0. For example, we could be finding the derivative of 2 to the x power. How do you do that? Well, we don't know. We haven't learned that yet. You could be finding the derivative of 3 to the x power. Again, we don't know how to do that. So whatever your base is, we're just calling the base a. Your base could be anything, as long as it's a number that is greater than 0. The derivative of that expression is the exponential expression itself multiplied by the natural log of whatever the base is. So we're going to show later on why that is the case. That just that turns out to be the case. Now, if you have the special situation where the base is e, remember e is a special number that we learned. In my curriculum, if I remember correctly, I think we learned it when we went over compound interest. We found that e was a very useful number. E is actually just a constant. And if you go to your calculator and you press the E button and press enter, it will say 2.718281828, and it'll just keep going on and on. It's an irrational number, but it is a constant. And if we use this formula to find the derivative of e to the x, then we get, well, let's write it over here. The derivative of e to the x is e to the x, right, that's this part, times natural log e. But natural log e is just 1. Now, why is that? Well, because natural log, remember, is just log base e. Okay, so the blue ln became natural log e. That's what it means. So if you want to find this expression, the value of this expression, what we're looking for is y, right? We're looking for whatever y is. But remember, the most important thing with logarithms is to be able to translate back and forth between exponential and logarithmic expressions. So the base is going to be e, the exponent is whatever the logarithm is equal to, and whatever's in the logarithm function, that goes on the other side of the equation. And so what is y? We can see what y is just by solving this equation. Obviously the exponent here has to be 1, which means that well, this exponent is 1 by exponent rule number 6. And so the only solution to this equation is y is equal to 1. That's the only way it could possibly work. So what does this mean? It means that natural log e is 1. So that's the explanation for why the derivative of e to the x is just e to the x. This is the only function where its derivative is equal to itself. And these are the formulas for the derivatives of logarithms. This formula is really not used very much in the calculus curriculum. So these two formulas are the ones that are really not used that much, but these blue formulas you're going to be expected to know. It's 100% guaranteed that you'll have to know those. There's a chance that you'll have to know these formulas, and so you really do need to memorize all 4 of these. But just be aware that these ones here are not really covered much in the curriculum. Now again, the derivative of this logarithmic function is 1 over x times natural log a, but in the special case where a is e, the natural log e just disappears in the formula because natural log e is just 1. So let's do some practice problems. I want you to take pictures of this information, and let's do a practice problem. So we're told to find dy over dx. The derivative of this expression is just 3 to the x times natural log 3. That's it. We're done. So pretty easy. The derivative of this expression is equal to 4 to the x times natural log 4. Very easy. So the good news is that these formulas are really easy to remember. The bad news is that you're almost never going to use these. So it's difficult to remember them because students just don't use those very often in the curriculum. I'm going to give you one more chance to take pictures. Get a picture of number 17 and 18. And I want you to try number 19 and number 20. When you come back, we'll do it together. Okay, we're back. So the derivative is 7 to the x times natural log 7. That's it. All right, try number 20. If you got number 19 right, good. When you come back, we'll do it together. Okay, we're back. So the derivative is 5 to the x times natural log 5. You got that right? Excellent. That's how the formula works. That's how you find the derivative of an exponential expression. But now, we're going to need to use the chain rule because we have a function inside an exponential function. So when we find the derivative of this type of expression, it gets a little confusing when we use our explanation of the process that we use to perform the chain rule. For example, when we found the derivative of secant x, it was a little difficult using our explanation of the chain rule to do that. So just be aware that this might be a little confusing, but it's the best way to explain this. We're just going to use those 3 steps. We could refine our explanation of the chain rule a little bit in a little bit more precise way, but then that would just make things more confusing. So we're going to do it the same way we did in previous classes. We're going to find the derivative of the outside function. So I'm going to leave the inside blank. Remember, this is how we find the derivative. We just rewrite the expression, and then we multiply by natural log of whatever the base is, right? So that's kind of the derivative of the outside function. But remember, step 2 is to keep the inside function. And then step 3 is to multiply by the derivative of the inside function. So it's a little confusing, but it's really just the same thing that we did when finding the derivative of composite functions in the past. So we have 6 to the x squared power times natural log 6 times 2x. That just becomes 2x. And you don't want to think that the 2x is inside the natural log function, so it's probably best to write parentheses. And we should really move the 2x in front. 2x 6 to the x squared times natural log 6. You can use parentheses if that's kind of a confusing expression for you. You can use parentheses around the 2x if you want, or you can write it around the expression there, but it's probably fine to leave it in that form. Okay, so let's try another one of these. We have an exponential expression. We're going to find dy over dx. So we're going to find the derivative of the outside function, but then we're going to keep the inside function the way it is. We're not going to change it. Remember, that's the chain rule. Derivative of the outside function, keep the inside function unchanged, and then we're going to multiply by the derivative of the inside function. So we get negative cosecant squared x for the derivative. And we can take this negative and put it out in front. That's traditional to do that. And to avoid confusion, I'm going to write the natural log in parentheses. And so there we go. So that is the derivative. I want you to try number 23. Use 21 and 22 to help you, and when you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Go ahead and try number 24. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, so now we're going to find the derivative of e to the x, the function e to the x. And remember, if you have your formulas right in front of you, you know the derivative is simply e to the x. Now remember, if you find the derivative of an exponential function, it's whatever the exponential function is times natural log e. But the problem is natural log e is just 1, so we don't need to write it. So you need to remember that the derivative of e to the x is just e to the x. It's very important to remember. Now, I don't want to insult your intelligence here, but unless you actually do this yourself, it's not really going to internalize. So I want you to do number 26. Make sure it goes into your brain. I want you to remember the derivative of e to the x is e to the x. So go ahead and try 26. When you come back, we'll do it together. Okay, we're back, so there you go. Again, I'm not trying to insult your intelligence. It's just unless you do it yourself, it doesn't really, your brain is not going to recall what we just did. So now we move to the chain rule with our e to the x function. So, and I guess I should have called this dy over dx. That was the instructions. It's easier to write y prime, but we're asked to find dy over dx. But here we're told to differentiate, so that means we can use any notation that we really want to use, as long as it has a y in it, because this function is defined to be y. So I'm going to use y prime. It's easier to write. So I'm going to find the derivative of the outside function, which is basically just e, while we keep the inside function unchanged. And then I'm going to multiply, and by the way, this would be part of the outside function also. But again, natural log e just is 1, so it doesn't need to be written. Then we multiply by the derivative of the inside function. So again, we use the chain rule. But again, natural log e is just 1, so we don't really need to write it. So we can get rid of that. So again, we're just using the 3 steps of the chain rule. the derivative of sine is cosine. And so there you go. We're done. So again, when you find the derivative of e to the x, it's just e to the x. That's the derivative. But if you have an inside function, that inside function needs to stay there because that's what the chain rule tells us. Keep the inside function unchanged. But you then have to multiply by the derivative of the inside function. So again, we're using the chain rule. Very important to understand the chain rule. So I want to do one more problem before you try one of these on your own. Now, before we find the derivative, let's change this to 2e to the x to the 1/2 power. Remember, we can't find the derivative of a root expression unless we change the form. So now we're going to find the derivative of that expression, and this is just we're going to use the constant multiple rule. I guess I can write one more step. It's the constant multiple rule. And so the derivative of the outside function, we need to find that. So that's just going to be e. But we have to keep the inside function unchanged, so nothing happens to that. But then we have to multiply by the derivative of the inside function. Again, that's the chain rule. And we could also write natural log e. Again, we're using that same formula for exponential functions. The derivative of the outside function is e and then natural log e. That's part of the outside function, but natural log e, again, just is 1, so we don't really need to write it. I know this stuff is strange, but you're gonna learn fluency in this as we continue throughout the course. Now, we can just change that blue expression back to root x. That's easier to write because we're not really going to do anything to the inside function. And the derivative of x to the 1/2 is 1/2 times x to the 1/2 minus 1. So notice that 2 times 1/2 is just 1, so they cancel out. And so then we have 2e to the root x. Whoops. We have e to the root x, and then x to the negative 1/2 power. But remember, we can't leave our answer with a negative exponent, and we can't leave our answer with a fraction exponent. So we're going to bring that down to x to the positive 1/2 power. And so we got rid of the negative. That's the first thing we need to do. We got rid of the negative exponent. But then we need to deal with the fraction exponent, so we change that to root x. So there you go. So I want you to try some problems like that. So get a picture of 27 and 28, and I want you to try number 29. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 30, and be aware that you're going to have to change this expression so you don't have to use the quotient rule. Change that expression first to e to the x to the negative 1 power. You can use the quotient rule if you want to, but Be a lot easier to find the derivative in this form. When you come back, we'll do it together. All right, we're back. So if you got that right, good job. Okay, so now we're going to find the derivatives of logarithmic functions. So again, we have a formula for this, so it's going to be 1 over x times natural log of 2. The 2 comes from there. And that's it. It's that simple. These are the formulas where you really don't use them very often in the calculus curriculum, to be honest with you. These logarithm formulas, again, finding the derivative of a to the x and finding the derivative of log base a of x, you don't really use the derivative formulas for these very much. But the special cases, e to the x and natural log x, you do find the derivative of these expressions quite a bit. So just be aware. So the formula, again, is 1 over x times natural log 5. 5 came from there. It's always going to be natural log. So it's that simple. Again, the good news is that the formulas are very simple. The bad news is you have to memorize them, even though you really don't use them very often. So try number 33. When you come back, we'll do it together. All right, we're back. So if you got 1 over x times natural log 9, good job. Try number 34. When you come back, we'll do it together. All right, we're back. So if you got 1 over x times natural log 12, excellent. So again, those formulas are very easy to use. But what if you need to use the chain rule? So when we use the chain rule in this situation with this function, our explanation of the process of the chain rule kind of starts to break down. It doesn't really work that well. We need kind of a more precise understanding of the process by which we use and explain the chain rule. So we know that when we find the derivative, it's 1 over x times natural log 3. But we have an inside function, so where does that go? Well, it goes inside this expression, meaning you plug it into x. So that's actually a better way to describe the chain rule, is you're actually taking the function that is the derivative of the outside function and you're plugging in the inside function. You can think of it as just keeping the inside function unchanged, but the problem is because our derivative looks so much different than the original expression, that kind of starts to fail as an explanation for the chain rule. This is a better explanation. We're just plugging in the inside function into whatever we get for the outside function, but the problem is that is really confusing to understand, and that's why it's not really described that way. The process of the chain rule, that is not really described that way. But in this case, we have no choice. We kind of have to describe it that way. So we found the derivative of the outside function and we kept the inside function, and now we're going to multiply by the derivative of the inside function. So again, that's a more precise explanation. We're plugging in the inside function into the derivative of the outside function. The reason we don't use that explanation is because it makes things more complicated when you first learn the chain rule. So we're going to have to use parentheses around the cosecant x so we don't confuse that. So we don't think natural log is in the cosecant function. The derivative of cosecant x is negative cosecant x times cotangent x. And we do need to use parentheses. And then our final answer is going to be negative cosecant x times cotangent x over cosecant x times natural log 3. And you can see that the cosecant x's cancel out, and we're left with negative cotangent x over natural log 3. All right. So let's try another one of these. Before we do anything, we're going to need to change the form of that fraction. We don't want to use the quotient rule, so I'm going to change that to negative 2 times x to the negative third power. Now we can just use the product, or the power rule. So the derivative is 1 over x times natural log 20, right? That's the derivative of the outside function, but we have to keep the inside function. So we're going to replace x with the inside function. But again, it doesn't really work that well to explain it that way. You can think of it as we're plugging in the inside function into the outside function. But if you want to, you can think of it as just keeping the inside function. And then, of course, we're going to multiply by the derivative of the inside function. So it's the same 3 steps in the chain rule. So we have kind of a weird expression here. This is going to be negative 2 over x cubed times natural log 20. Then we have 6x to the negative 4 power. And so we can, there's a lot of different ways to simplify this. I'm just going to keep this as negative 2x to the negative third power. I think that'll be easier to deal with it that way. So now we're going to move that 6x to the negative fourth power up in the numerator. There's a lot of different ways that you can simplify this. I'm just choosing the first way that comes to my mind that seems easy. Then you're going to use exponent rule number 2. We're going to subtract, so negative 4 minus negative 3 is negative 1. So we get negative 3x to the negative 1 all over natural log 20. But we're not allowed to have a negative exponent, so we have to bring that down. There may have been a faster way to do that, but so we get negative 3 over x natural log 20. So there we had a few examples where we had to use the chain rule. Okay, so I want you to get a picture of numbers 35 and 36, and I want you to try 37. When you come back, we'll do it together. Alright, we're back. So let's try another problem like that. Go ahead and attempt number 38, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so now we're going to find the derivative of natural log functions. Remember, natural log x is the same thing as log base e of x. So all we're doing is just using the same formula. It's 1 over x times natural log of whatever the base is. In this case, the base is e, right? So it'd be natural log e. E is just a constant. But remember, natural log e is just 1, so that green expression just disappears. And so we're left with 1 over x. So you can just memorize that the derivative of natural log x is 1 over x. That's the way that mathematicians really think of this. It's just something that you memorize. So again, I don't want to insult your intelligence here, but unless you do a problem and see for yourself, it's hard to internalize this information. So try number 40. When you come back, we'll do it together. Alright, we're back. If you got 1 over x, correct. Again, I'm not trying to insult your intelligence. I just want you to internalize this. So now we're going to find the derivative when you have a function within the natural log function. And we're just using the same formulas. remember, natural log is the same thing as log base e. Alright, so if you want to find the derivative, it's just 1 over x times natural log e. But remember, we have to keep the inside function. So we have to write secant x plus 2x. We have to keep that unchanged. And again, this is where our understanding of the chain rule kind of breaks down. We really consider this to be f prime of g of x, meaning we're taking this inside function and putting it into the we're making it the input of the derivative of the outside function. That's very confusing to think about it that way. Also, again, natural log e is just 1, so that's just going to disappear. But we have to use the chain rule. So we found the derivative of the outside function. Well, we kept the inside function. And then we're going to multiply by the derivative of the inside function. I know that this is very strange, but it's just going to be like second nature to you as you do more and more of these problems. So let's well, we can get rid of natural log e because that's obviously just 1. And then the derivative of secant plus 2x, secant x plus 2x is secant x tangent x plus 2. And I'm actually going to write that as a derivative up here. I'm just going to copy that because we're going to demonstrate an important principle here. So I just moved it up into the numerator. That's perfectly legal. So the final answer is secant x tangent x plus 2 over secant x plus 2x. So that is the final answer. So I want you to notice something that occurred here. We have a function within the natural log function, and we found the derivative of this expression, but the derivative just ended up being the derivative of the inside function divided by the inside function. Again, the derivative of the natural log of some function is equal to the derivative of the inside function divided by the inside function. That's true for any natural log function. And we call this differentiation formula number 13. The derivative of the natural log of some function is equal to the derivative of the inside function divided by the inside function. This is the result of combining differentiation formula number 12 with the chain rule. It just turns out that this is true. Now you're going to see this written with u's. Often you'll see the rule written using u. So this means g prime and this means g, but I find that to be very confusing, and I think a lot of students find that to be very confusing. So I'm not going to use that form of the rule, but just be aware that you may see that u is considered to be a function. So we're not going to find the derivatives of just any logarithm, any base logarithm, very often, but we are going to find the derivatives of natural log functions quite often in the calculus curriculum. So it's very important that you memorize this this result here. So take a picture of that, and let's try some practice problems. So we have a function inside the natural log function. So our formula tells us that the derivative of this expression here is just the derivative of the inside function divided by the inside function. A lot of students are kind of in disbelief that it could be that easy, but that's actually how we find the derivative of an expression like this, a composite natural log expression. So we have 4x cubed, that's the derivative of the inside function. That's over 1 plus x to the fourth, and you're done. It's that easy. So let's try another one. So again, we have a function inside the natural log function. And so the derivative of this overall expression is equal to the derivative of the inside function divided by the inside function. It's that easy. So we get 7 over 7x because the derivative of 7x is 7. But we can simplify that by canceling out the 7's, and we get 1 over x. So there's another example. Again, this is a really, really important formula that you're going to use quite a bit. And so let's try one more of these types of problems before you try one on your own. So y prime is equal to the derivative of the inside function divided by the inside function. So the derivative of the inside function is cosine x. Derivative of sine is cosine x. But at this point, we really need to use a trigonometric identity. Remember, this is one of the ratio identities. Cosine x over sine x is cotangent x. So again, you're going to be expected to remember those trigonometric identities. So I want you to get a picture of all this information here, number 41, and differentiation formula number 13. And I want you to use numbers 42 through 44 to help you do number 45. Try number 45. When you come back, we'll do it together. Okay, we're back. All right, so if you got that answer, excellent. Go ahead and try number 46. When you come back, we'll do it together. All right, we're back. So if you got that answer, excellent. Okay, go ahead and try number 47. When you come back, we'll do it together. All right, we're back. If you got that right, perfect. Go ahead and try number 48. And when you come back, we'll do it together. All right, we're back. If you recall, sine over cosine is tangent x. That's one of our trigonometric identities. Okay, so go ahead and try number 49. And when you come back, we'll do it together. Okay, we're back. So there you go. got that right? Good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and the exponent rules, and screenshot number 2, number 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, but don't go before you get your homework. So here's screenshot number 1 of the homework, and screenshot number 2, and number 3, 4, and 5, but don't go before you get the answers. It's not enough just to attempt the homework, you must do it correctly. So here's the answers. Get that homework done completely and correctly and neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.